Hello community, thank you for your interest in our work RoboTAG end-to-end robot configuration estimation via topological alignment graph. We present RoboTAG, a 3D vision method for the visual pose estimation problem. We want to use computer vision methods to solve pose estimation problems under articulated geometric constraints. Specifically, our method setting is, given an input image of a robot arm, we can output camera pose of this image and estimate the joint angles of each articulation in this robot arm. Visual pose estimation is an important research problem, and many papers have explored using deep learning models in computer vision. Some classical work train a network based on 2D visual backbones and apply prediction heads on the extracted features to get the poses, that is, camera pose and joint angles. They achieve stable and reasonable results on most cases. However, in some cases where the joint angle is large, the camera pose is not typical position, or some of the joints are occluded, the performance degrades. This limits their application in real-world cases where situation is not always controllable. We attribute this to the ill-pose problem of predicting full information from 2D image, which leads to ambiguity and a lack of stability under occlusion. We propose to solve this problem with more prior information. One natural direction is to leverage the 3D geometric constraints of articulations. In our robot arm image problem, one of these constraints is the physical structure of this given robot. No matter how poses change, the distance between the two joints are fixed. That is, the arm's length. 2D methods cannot understand this length easily, but 3D models can. We want to introduce 3D models into the pose estimation system to make full use of the geometric constraints. The more constraints we use, the stabler the prediction will be. Then I'll specify how to integrate the 3D network and the priors. Previous methods use feed-forward networks to predict all the states of the system, like joint angles, so their structure is a tree from the 3D features at the roots towards the predictions at the nodes. The structure is shown in Figure A. When we introduce another backbone, there will be many states that can be arrived from different passes. For example, the 3D position of the key points can be predicted by the 3D network directly, or they can be arrived at by using the predicted pose and the robot forward kinematics. We model them as different states which share the same meaning. We call them duplicate states. Then we can build our graph named Topological Alignment Graph containing all those states. With this method, we can instantiate this topological alignment graph. Note that there are many pairs of sets of duplicated states thanks to our new information from the 3D backbone. We can leverage this duplication for supervision signals. That is to say, we want the duplicated states to be as close to each other as possible. We want the prediction results from the 3D backbone similar to that coming from the 2D backbone or a hybrid of both. We thus set alignment laws between the duplicated nodes, and the gradient flow will influence all the neural networks in the closed loops containing that alignment. For a clean definition, please refer to algorithm 1 and 2 in the main paper. Quantitative results show that we have a 1.2% growth on AUC of ADD on the DREAM dataset. And qualitative results show that we can do better on those extreme cases, achieving better stability. Takeaway messages. First, incorporating geometric priors into a visual pose estimation task is beneficial. Second, topological alignment graph is an effective way of fusing features from different backbones. Generally speaking, leveraging constraints and priors in computer vision is helpful. We also show some limitations of our paper. Though TAG exhibits superior generalization, performance on the in-distribution set is slightly lower than existing methods, which suggests that the 3D consistency loss is less effective for in-distribution fitting when supervision signal is available. Though the accuracy for joint angle prediction and the global 3D posture is improved, the joints near the gripper, whose impact on the 3D structure is weak, still have larger deviations. Solving these problems might be an interesting direction. Thank you for watching.